We used a spring in the projectile lab, but we didn't study springs. So we spend a lot of time looking at springs, mass on springs, because it's a really useful physical model. Okay, you can model atomic vibrations, mass on a springs. So if you click on that link, it takes you to a page that shows a molecule where it can vibrate, analogous to a mass on a spring. Okay, so here's the pictures that we use. Here's my spring. That's my spring. Here's my mass. Okay, this thing can oscillate back and forth. All right, and this is my relaxed position. Okay, so here's my spring. I know it's floating in midair, but there's my spring. Okay, the relaxed position. So the spring is not stretched or compressed. It's the equilibrium position. In the force chapter, equilibrium means net force equals zero. Think of in chemistry, when the reaction is done, nothing is happening. Okay, system's in equilibrium. So this is the relaxed or equilibrium position. So net force is zero. Okay, and I want to look at the spring force. So I grab the spring and I stretch it. I'm pulling it. Okay, so I want to find the spring force, and the spring force is the force exerted on my hand by the spring. So as I pull it to the right, okay, as my hand is moving to the right, the spring force is trying to pull my hand backwards. Okay, if I compress the spring, okay, so I'm pushing, okay, I'm pushing the spring to the left. Okay, the spring force pushes backward or pushes back on my hand to the right. Okay, and there's a relationship called Hooke's law, and Hooke's law says that the spring force is proportional to, that symbol means is proportional to the displacement from equilibrium. So this means that if I want to squish the spring a certain distance, it costs me a certain amount of force. If I want to triple that distance, turns out I have to triple the force. They're proportional. Okay. Let's see. The proportionality constant is called K. That's the spring constant. So when we draw our little spring pictures, always put the spring constant K there so we know that it's a spring. Okay, so what is that spring constant? Well, if I solve this for K, okay, so K would be F over X, so it would have units of newtons per meter. So K is just a measure of how stiff the springs are. Okay, so imagine if you took your pen apart, you have a little spring in there. Okay, so it's a measure of how much force is required to stretch the spring by a certain amount. Okay, if you have an older iPhone or an older phone or an iPad has a button, okay, you press on the button. Okay, so they designed that so you don't have to stand on the button to press it to go back to the home screen. So that button has a certain spring constant associated with it, probably. Okay, now the important part is the minus sign. Where did that come from? Okay, so the minus sign means that the spring force is opposite the displacement, okay, when the spring is moved from its relaxed position. Okay, so go back here in this picture, spring's at its relaxed position. If I displace the spring to the right, spring force is back to the left. Here, if I displace, in compression, if I displace the spring to the left, spring force is opposite that to the right. Okay, if I didn't have the minus sign, if I left it off, okay, that would say here that if I pulled the spring to the right, okay, if X was to the right, then the spring force would keep stretching the spring to the right, and that makes no sense. Okay, so the spring force has that minus sign. Okay, so the minus sign also indicates that it's a restoring force. If I move the spring to the right, okay, when I'm stretching it, move the spring to the right, spring force wants to restore it back. For compression, if I move the spring to the left, spring force in a direction to restore it back. That's what it means, it's a restoring force. Now, it's okay to call Hooke's law, or to call this Hooke's law. Okay. Some people say, well, just this relationship is Hooke's law, but it's okay. You can point at that and say that's Hooke's law. But basically, the spring force is proportional to the displacement, okay, and the proportionality constant is the spring constant. Okay, so what I did here is, here's my spring, relaxed position. And then underneath my picture, I drew a graph of the spring force. Okay, so remember the spring force is minus kx. Imagine algebra class, you graphed y equals minus 3x, right? It'd be aligned with a negative slope. Okay, so your spring force is aligned with a negative slope. So if I put in positive values of x, that's over here. When x is positive, okay, when x is positive, positive times a negative gives me negative spring force. That says the spring force is negative. That's a negative value here, points to the left. When x is negative, okay, over here, if I put in a negative number for x, a negative times a negative is positive. That means the spring force points to the right. Okay, so you can see the way I drew the arrows, it almost looks like it wants to restore it back toward equilibrium. Okay, now how would you find the spring constant for your spring? Well, what you actually do is you hang the spring. So here's my spring hanging from the support, okay, and that's my relaxed position, nothing attached to the spring. Now I attach a mass to the spring, okay, and I slowly let it down, and it's just sitting here. It's not moving. Okay, acceleration 0. So essentially it's a 5-step method. I picture, forces, regular coordinate system. Okay, I didn't really draw. All right, nothing to break up. So I'm going to apply F equal ma to the little hanging mass. So if it's not accelerating, the net force is 0. So that says the spring force that points up equals to mg that points down. Okay, but the spring force in magnitude is kx. So right here where I have the spring force, I can just write kx. Okay, and then I can solve that for the spring force. So if I know the hanging mass, I know g, and I can measure this distance x, okay, the distance that the spring stretches, then I could calculate my spring force. Okay, so maybe in lab you would find a certain spring force, and it would be in units of newtons per meter. Okay, so we've done straight line motion, we did circular motion, then we did rotational motion. So now we're going to continue those concepts into the idea of oscillatory motion or simple harmonic motion. Okay, so we're going to see that circular motion and rotational motion are closely associated with things that oscillate back and forth. Okay, so first thing we want to look at is the concept of periodic or harmonic motions. Okay, so any motion that repeats itself in regular time intervals. Okay, so the key thing, it's about a time interval. So if it repeats the motion in regular time intervals, it's said to be periodic motion, okay, or you can call it harmonic motion. Both of those mean the same thing. So here's a couple examples of things that are oscillating, okay, or repeating their motion in regular time intervals. Okay, so here you have a pendulum. Okay, here's a mass on a spring. All right, what is this thingy? Right, that's a comet. Okay, so it was Sir Edmund Halley was, I think, the first person who discovered that comets are periodic. Okay, so Halley's comet is in orbit around the sun, and it comes by, I think, once every maybe 75 or 76 years. And I think the last time it came by was about 1986. So we saw these objects that repeated their motion in regular time intervals. That's called harmonic motion. Okay. Another type of motion that we're going to look at, or a particular type, is called simple harmonic motion. And we always abbreviate that with SHM. Right? Okay, so a body is said to be in simple harmonic motion if the position, okay, now the position can be x, like look down here, it could be like a mass on a spring, okay, it has a certain position, x, okay, or theta, and we'll see in a little bit, theta could be like a pendulum going back and forth, all right? Okay, so just think about its position, whether it's a pendulum or a spring. So if you can write the motion in this form, then the motion is said to be simple harmonic motion. Okay, so I want to look at a few of the features in this. Okay, now, first of all, there's a cosine there. Okay, so most people said they took trig. If not, no big deal. Okay, we've done trig all semester. All right, so because if you go to some other books or maybe look online, they might start this with a sine. You might be asking, well, why do we have a cosine? Why do they have a sine? Okay, so if you remember down here, okay, so the cosine function, all right, looks like this. It starts high up here, and then it goes low, all right? Whereas the sine function, okay, starts at 0 and then goes high, all right? Okay, now, why would we use one or the other? Okay, so let's say if I have a mass and spring system here, okay, and you're holding on to it, and you're going to let go at time equals 0, all right? So let's say it's stretched out to 3 meters. Obviously, 3 meters is 10 feet, but I wanted to use m instead of cm for centimeters, have less symbols. So you let go of it here, okay, and that thing is going to oscillate back and forth like this. 1, whoops, 3, like that. 1, 2, 3, 4, 5, 6, and so on. So that thing's going to oscillate back in simple harmonic motion, all right? Now, in this picture here, okay, if you let go at time equals 0, okay, it starts out up high at the amplitude, okay? So it starts out up top, all right? And then as you let it go, it'll pass through the 0 point right there, okay? And then it keeps going out here and gets to the low point, okay, or the minus point, and then it comes back to 0 right there, and eventually it'll come back to where it left your hand. Okay, so that would be a cosine function, okay? Now, up here, I have a function. Let's say this system here, this system is already oscillating back and forth, so someone pushed it, set it into motion, okay? And then you walk into the room and you pick up a timer, okay? And you decide to start your timer when it's at some position, maybe right here, okay? So maybe right there or something like that. Well, it's not at the peak. Maybe it starts right there, okay? So it starts here and it's moving that way. So it starts here and then gets up to the high point, okay? Okay, so it didn't start at a high point and it didn't start at a low point, okay? It's at some intermediate point, right? So it's a sinusoidal curve, and you could call that either a sine or a cosine, okay? So it doesn't matter. Okay, so here we're going to stick with a cosine. Okay, now, remember, if you, on your calculator, okay, before you hit the cosine button, okay, you put in a number and you hit the cosine of numbers for an hour. Sit there and hit a whole bunch of numbers. The biggest the cosine ever gets is a 1, okay? And the smallest the cosine ever gets is -1, right? Same for the sine. Okay, the biggest the sine ever gets, if you put numbers in the calculator and hit the sine button, you get a 1. Smallest you ever get is a -1. So these sines and cosines go back and forth between +1 and -1, right? So this amplitude, okay, in the picture, the amplitude is the height from the midpoint all the way to the top, okay? So that's what this quantity represents. You might remember that from trig class. So the thing in front is called the amplitude. Now, the reason I'm using this symbol, okay, this symbol, a lot of times you might see that written as x max, okay? I wrote that as x max. So that's what the symbol x sub m stands for. It's just I'm not spelling out the word max, okay? So that represents my amplitude. And by definition, the amplitude is always positive. It's a positive number. Okay, and then the other ones, we'll see in a little bit what they represent. Okay, so if I go down here I have a spring system, okay, and someone's already compressed it. So it's sitting right there. Maybe they compressed it 5 centimeters, okay? It's already sitting there, and then they're going to let it go at time equals 0, all right? So that means it starts at -5 at point A, okay, eventually gets to point B, and then it passes point C and keeps on moving out to point D, okay? Well, that curve looks like this, okay? That looks like not a sine, because a sine starts at 0, okay? This thing starts not up there, but starts down there, okay? So it looks like a cosine, okay? It looks like a cosine, but it's flipped. It's inverted, okay? So that's going to be a cosine function, okay? The amplitude is 5, okay? Got to be careful, okay? The amplitude is not -5, okay? The amplitude is 5. So in trig class, okay, these trig functions we'll see again were derived on the unit circle. So this amplitude, okay, think about when this is all the way up here at 90 degrees, okay, that amplitude is really just a hypotenuse. And a hypotenuse, by definition, is always positive. Remember, a squared plus b squared is c squared. Okay, so that's why the amplitude, think of that height, that maximum height right there is a positive number. Okay, so that amplitude has to be positive. So the amplitude, okay, the amplitude is 5. That's what I have right there. Okay, the amplitude is 5. So we can write that as, there's my amplitude is 5 centimeters. Okay, the function looks like a cosine, but I have to put a minus sign. Okay, it's a flipped, okay, it's that cosine, but it's flipped. It's inverted by -1. Okay, so I know the minus sign goes there because if I put in at time equals 0, okay, here's where I let go. Okay, right there at time equals 0. Okay, if I put in a 0 right there, on your calculator, a cosine of 0 is 1. So if this is 1 and that's a 5, you need the minus sign. Okay, so this function right there describes that mass and spring going back and forth. So the amplitude is 5. Okay, now, this thingy here, okay, that's omega. In the previous chapter, we called that the angular speed. Okay, all right, that was the angular speed. Now we're going to call it, we'll see, it's called the angular frequency. Okay, now, if you remember what the omega does, okay, what's the job of the omega? So let's say if I graph this function here, this just has this form. So the function has this form, right? And omega I put in right there was 1. Okay, all right, so let's say it just has, the graph looks like that. Okay, now what does that omega do? Well, if I change omega to 3, if I put in a 3, remember what that does? It just has more wiggles in the same number of same period of time. Okay, so it oscillates or wiggles more frequent. Okay, so that's why omega is now called the angular frequency. Okay, so that's what that thing does. All right. Now the other thing in there, okay, this is called phi. Okay, that's the phase shift. Okay, what does that thing do? All right, so let's say I have this mass and spring system. I pull it back to point A, and I'm going to let it go at time equals 0. Okay, so at point A at time equals 0, okay, it's up here at x max equal 1 meter. Okay, so that function would look like this. It's a cosine. So if I put in time equals 0, okay, cosine of 0 is 1, and sure enough, it starts there at that height of 1. Okay, so I let this thing go at time equals 0. It goes from A to B to C, from A to B to C. So starts high and goes low to C. Okay, well, what if instead, okay, I let go here, let go at the same place, but someone didn't start their timer, okay, until this thing passed through point Q. Okay, so that means the graph would look like this black line here. Okay, so I let it go right there, but I didn't start the timer until it got to point Q. There's point Q right there. So it starts here, okay, at Q, and then it passes to P. Okay, so the function doesn't start up here, okay, it doesn't start high, and it doesn't start at 0. So this function kind of looks like a cosine, right? It looks like the blue cosine above, okay, but it's been shifted to the left. Okay, so that's what the phase shift means. This thing's been shifted over to the left. Okay, why do we have this function in the first place? Okay, remember the earlier chapter, we had the car at the light. Okay, you put your foot on the gas pedal, the car accelerates. And this is equation number 2 that told us where the car was at a certain time. Okay, equation number 1 told us how fast the car was going at a certain time. Equation number 3 told us how fast the car was going at a certain place. Okay, and the fine print for those was that they held only when the acceleration is constant. Okay, well, now our problem looks like this. You have a spring, okay, you let it go at time equals 0, this thing's going to go back and forth, okay, and we want to know, okay, well, where is the spring as a function of time? Okay, how come I can't use that expression to calculate the x coordinate as a function of time? Okay, well, remember, that only holds when the acceleration is constant. Is the acceleration of that object, that little block going back and forth, or if I have a cart on wheels, is that acceleration constant? Okay, No, because it does this. Okay, it starts here from rest, it speeds up, slows down, speeds up, slows down, speeds up, slows down, speeds up, slows down. And it goes back and forth. Acceleration's not constant. Okay, so we can't use, okay, this equation here that gives us the position of the car from chapter 2, constant acceleration. Okay, so our equation number 2, okay, for this little block is that one. Okay, that tells us where the block is at any time. Okay, and its position is sinusoidal. Okay, so here's the person in the car. As time goes on, okay, they're all the way down the road. Okay, this thing just oscillates back and forth. Okay, it's repeating its motion. All right, so this equation takes the place of number 2 in the older chapter. This tells us where the car is at a certain time.